Hello everyone, this is going to be section 2.6 in limits at infinity. So to show the difference between limit at infinity and infinite limits, let's consider the function 1 over x squared. Notice this is the graph of the function 1 over x squared, and the first thing that we're going to see is what happens if we approach 0. Notice we start in 0.1, and so let's take some values in x and see what happens with the formula of 1 over x squared. In this case, if I plug 0.1 in 1 over x squared, this 0.1 squared is going to become 0.01, and no matter if it's positive or negative, this is going to give me 100, okay? Because it's like 1 divided 1 over 100. So that's going to flip around the 100, and it's going to give me that. If I get closer, if I use 0.01, then now that's going to produce a 10,000. And if I get more closer, that's going to produce a million with 0.01. And in general, the more that I approach 0, the more that f of x is going to approach infinity. So what I can say here is that the limit when x goes to 0 is infinity. And you can see that graphically here. The more I approach to 0, the larger the values are going to be. Similarly, by the left side or the right side, they're going to produce both infinities, and so that's why the whole limit is infinity. Okay? Now, with limits at infinity, the opposite is going to occur. The dependent variable is going to approach a finite number as the independent variable becomes arbitrarily large in magnitude. So as an example, now instead of approaching 0, we're going to approach infinity. So we're going to take larger and larger numbers, and we're going to see that the image f of x is going to approach a number. We're going to use actually the same function, 1 over x squared. So notice that if I use 10, 1 over x squared becomes 0.01. If I grow larger, let's say 100, then 1 over x squared becomes 0.01. And if I use 1,000, it becomes 0.0001. And in general, the larger the number I chose, the closer am I going to get to 0. So in this case, what we can say is that in both cases, limit when x goes to infinity and limit when x goes to minus infinity, then I'm going to obtain a 0. Notice that here is independent of the sign. It doesn't matter if I'm picking positive or negative. This is just going to produce a very small value that is going to go to 0. Okay? The limit at minus infinity can be, in some occasions, a bit different from the limit when I'm going to infinity. And notice that what I do is I pick a larger and larger value. When I'm approaching infinity and I want to do this analytically, so with table of values, here what I do is I pick values that are larger and larger. So this is what we call a limit at infinity, in opposition to the one before, which was an infinite limit, which is when the limit is actually infinite. Okay? So that's going to be the topic of discussion of this section and the next. Okay? Just to show you another example of these two scenarios occurring with the same function, notice this function here. If we think about infinite limit, we're going to see that when x goes to a, when we're approaching a, then by the right side and by the left side, both the function is approaching infinity. So I can say that y approaches infinity when x goes to a. On the other hand, if I'm approaching minus infinity now, if I'm going further to minus infinity, the function is going to approach certain value L. And so that's why we say that the limit at minus infinity is L. On the other hand, if I go to infinity to see what happens, I'm going to see now that the more that I approach larger values, the more that the function is going to approach certain value m. And so notice, as I mentioned before, the value at infinity is different from the value at minus infinity. Now, let's see the definitions of this. So suppose we're near a point A, and if f is growing arbitrarily large for all sufficiently close but not equal to a, we're going to write that the limit when x goes to a of f of x is infinity. If f of x is growing arbitrarily large in magnitude but negative for everything that is close to a, then we can say, well, the limit when x goes to a of f of x is minus infinity. If let's say the limit of f of x when x approaches a is negative infinity in one part and positive infinity in the other one, then the limit is not going to exist. Okay? Now, another example of this. So, for example, when x is of the definition. So, when x is approaching a in this case, f of x is growing arbitrarily large. So, you can see that the values are getting big and big by the right side and by the left side. So, in this case, we can say that this goes to positive infinity. Now, to negative infinity is the opposite. It's growing arbitrarily large in magnitude, but negative. And so we're going to minus infinity. So the graph is very helpful to show us when that happens. At least it's very clear from the graph. When we have the functions, then we have to use an analytic method to let that happen. But now, just to check an example, a different example, let's analyze a function into different points. So let's analyze the function x over x squared minus 1 squared, and we're going to analyze that in 1 and in minus 1. We're going to check what happened in both places. So now notice that when x is approaching 1, this is actually going to go to infinity. Why? Notice that if you actually start approaching values over here, this is going to go big numbers. This is going to get you big numbers, and it's going to be positive because you're approaching a positive number here, and below is going to be positive as well. So you can see that this is going to go to infinity. On the other hand, if I'm approaching minus 1, notice that I'm taking negative values, minus 1.1, minus 0 point something when I'm approaching over here, but the images are still very big and negative thanks to this x. So that means that this limit when x goes to minus 1 is going to go to minus infinity. And you can say, well, so how do I check this? How can I check that these values are going where they're supposed to go? And the answer is that you can always make a small chart that is telling you that. So you can say x and f of x, and so we want a couple values. Let's say we want to approach 1, right? And so we want to do it by the left and by the right. And so 1.01 and 1.1. I can test with that. And I can test with 0.99. And I can test with 0.09. Yeah, I can use those particular values. And so let me just get me a calculator, and let's check that graphically. So first, I'm gonna check the function f of x, and just give me a second. Okay, let's use this calculator here. So we can see the function x over x squared minus 1 squared. So that is f of x, but I can check with the values. So for example, I can have f of 1, which is going to be undefined, but I can check f of 1.1, and I can check f of 1.2 or 1.01, and I can check f of 1.0001. And so you can see that this value every time that we get is larger and larger, but positive. Now I can do in this three values, I'm doing it by this side, I'm doing it by the right side. Now I'm going to do it by the left. So I'm going to take some values on the left side, so 0.9, and now f of 0.99, and finally f of 0.9999. So you notice that every time that I'm getting closer and closer, the value is getting larger and larger. So this means that this is going to go to infinity. Now if I'm approaching -1, so you notice that this was for this particular case. Now then, let me do it again with -1. Let me use another instance of the same. Okay, so I have the function in there again, and now I want to approach -1, so I'm going to do the same thing. So I'm going to do -1.1, and I'm going to do -1.01, and I'm going to do -1.0001. And so you can see the same behavior that we have in the one before, just the only difference now is going to be that the sign is negative. So we can see that that's going to minus infinity. And so this is essentially what we need to do when we're exploring around a number, what's going on. So we're doing in two different points, and 1 and -1, and we're creating the table of values to see what's going on. So that will be one way of analyzing the behavior of what is happening, just taking values and checking if it grows larger and larger. Of course, if you have the graph, you can see it, but if you have the table, you have a backing of your results. Okay. Now let's go with this same behavior but one-sided. Let's see what happens if something is happening just in one side. So suppose that f is defined for all x near a with x bigger than a. So I'm referring by the right side of a. If f become arbitrarily large for x close to a with x bigger than a, then we're saying that the limit by the right side is infinity. Okay. Similarly, we can have the one-sided infinite limit to be negative. We have x going to a by the right being minus infinity, or we can have this behavior in terms of the left side. So for example, limit when x goes to a by the left side is infinity, or minus infinity, and this is going to be defined analogously in the same way. Okay. So just to show how that will happen and that kind of behavior will happen is let's check one-sided infinity limits by the right. And so in this example here, we have that the function is only showing up on the right of a, And when we're approaching the right side of a, we can see that the function is going to infinity. We don't have anything on the left side, so we can only talk about the right side. So the limit when x goes to a of f of x is infinity here. And in this case over here is the opposite. The limit when x goes to a by the right side is minus infinity. Now, opposite case, we can do it by the left side as well. If the function is only showing up on the left side, this kind of behavior when approaching a, this function is going to infinity. As you can see, the limit when x goes to a by the left side is going to infinity. And in this case, the limit when x goes to a by the left side is going to minus infinity. So now you get an idea of how that will work. Now, in this case is that we have that when we're approaching certain value a, the limit goes to infinity or to minus infinity, then we can call the line x equals a vertical asymptote of the function. Okay. So those points, those are specific points that they have this behavior, whether it's by the right side or the left side as well, they're going to be asymptotes of the function. So just to show an example here, so we have that the lines x equals 1 and x equals 3 are going to be vertical asymptotes of the function g of x. G of x here is the function x minus 2 divided x minus 1 squared times x minus 3. So usually you will see the asymptotes because the asymptotes are also issues on the domain of the function. So you see this 3 is going to make this 0, this 1 is going to make this denominator 0, so that can happen. And so that's why we have asymptotes in here. Notice that in one, limit by the left side and the right side, they're both going to infinity. But in 3, we have that the left side limit is going to minus infinity and the right side limit is going to infinity. Okay? Now, finding infinite limits analytically is something that you can do with the tables. So just as I show you on the Desmos calculator, you can do that by calculating what's going on with each of the values. For example here, if you consider the fraction phi plus x divided by x, we can clearly see that this is going to have likely an issue in 0. 0 is going to be an asymptote. So we can kind of try and guess where the limit is going to land. So if we approach by the right side, notice we can start with values very close to 0, and then we're getting closer and closer. Notice that every time the number is getting larger and larger, so that means that we're approaching to 0 by the right. This is going to infinity. Okay? Now, also, you can probably guess that if we approach by the left side up to a certain point, then this can produce something different. So you can see that phi plus x over x goes to infinity as x goes to 0 by the right, but this is going to go to minus infinity when we approach by the left side. Okay, so you can produce the same table from the left side, and this is just going to produce negatives here below, and with those negatives, then the value is going to change, and it's going to become minus infinity. Now let's take a look at another couple of examples, and so for that I'm going to actually use the calculator since it's a little bit easier that way to create a table. And so first, let's going to use the function f of x equals 2 minus phi x divided x minus 3. Okay, so this is going to be my function, and we are curious in seeing what's going to happen when we approaching 3. Okay, so let me remove the other examples, and we care about what happens when we do 3 by the right side, and 3 by the left side. Okay, so essentially we're going to produce the same thing for both. We're going to approach right side and left side. So with this, I can do f of 3.1, and so you can see a negative in there. F of 3.01 and f of 3.001. So in here we're approaching by the left side, and you can see that the numbers are getting larger and larger but negative. So we can bet that by the right side this is going to go to minus infinity, which is the kind of behavior that we see here in the graph. You can see that there's an asymptote, and this is going to minus infinity here. Okay. Now we probably can use the same here to check on the right side, on the left side, sorry. And so we can use 2.9, and we can use 2.99. And so at this point we can already see that it's just growing positive and positive the more closer that we get, and it's getting larger and larger going to infinity, like the behavior here suggests. Okay, so that will be what we want to do when we're checking the table. You check values and see what's the behavior. Is it growing and growing, suggesting that it's going to infinity? What is the value? What is the sign? Negative, positive? Okay, so that's what we're concluding here. So one of them goes to infinity, the other one goes to minus infinity. Let's do a similar analysis with x minus phi over x. So x minus phi over x. Let's do another one here. Let's call it g of x. And x minus 5 over x. Clearly here the issue is 0. So we're going to use numbers that are closer to 0. So you can see it from the graph right away that probably the left side is going to go to infinity and the right side is going to go to minus infinity. Let's check that out by using let's say 0.9, and now let's use 0.99. Well, this is actually getting closer to 1, not to 0. So let's say 0.05, which actually it is getting closer to 0 now. And now let's use something much more closer to 0, 0.001. And so as you can see, it's growing. It's not growing as fast as we think it can. So probably this is going to grow really slow. So if we do 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, then at that point we can see that it's getting larger. Let me see where it gets larger here, that we don't need that value. Yeah, at this point we can see that it gets really large and negative, so it's going to minus infinity. And similar behavior is going to happen with g around a point like 0.1, but negative. So if I put the negative in here, notice that now it's going to become a positive number. And so every time it's getting larger and larger, approaching positive infinity. So on this side, we can confirm what we think, what we see from the graph. One side is going positive, one side is going negative. Sometimes you're not going to have the graphing calculator over there, so you can just inform yourself from the results in the table. This is a similar thing, cotangent when we're approaching 0. And so what's going to happen here is that we approach 0 by the right side. This is going to take us to infinity. And by the left side, it's going to take us to minus infinity. If you have the graph available, great. You can see it from there. If you don't have the graph available, make points nearby and start plugging into your calculator and see what the tendency is telling you. Okay? In particular, recall that cotangent is cosine over sine, and sine is positive when theta goes to 0. And so that's something that can help you out see where the sine is going. So the denominator is always going to be positive. Maybe the top is what is going to tell you if it goes to positive or negative. And so instead of checking the full cotangent, you might be able to just check the cosine and be done with that.